In this video, we'll be looking at how to graph reciprocal functions. Now, a reciprocal function is when you take a function, let's call it f at x, and the reciprocal is 1 over f at x. So the numerator will always be 1, the denominator will be that original function. Now we're going to start off with some observations, okay? So I have this first function here, just the line 2x plus 4, and then I have its reciprocal 1 over 2x plus 4. I want us to first look at the x-intercept of the original function. The x-intercept was -2. And if you look at the reciprocal, at -2, we actually have an asymptote. So let's actually see if that applies to my second function as well. The second set of functions we have is the parabola g of x and its reciprocal. The parabola had x-intercepts of -1 and +3, which I could have gotten from my brackets. And once again, yes, they do result in a vertical asymptote at -1 and +3. And for the last one, again a parabola, it had an x-intercept at -1, and we do in fact have a vertical asymptote at -1. So that is a great starting observation. The x-intercept of f at x becomes a vertical asymptote on 1 over f at x. Great. Let's see something else. Now, there are parts of the function that are in the positive region, parts that are in the negative. And when I'm talking positive, negative regions, I'm talking about y coordinates. So right here, my function is in a positive interval to the right of -2, and it is also positive in that same region. Here, positive regions, and they're also positive on the reciprocal. This whole function is pretty much positive, except at that x-intercept, and same thing with the reciprocal. Now, the negative side, here's a negative region, it's negative on the reciprocal. Negative, negative on the reciprocal. So wherever your original function is, above or below the x-axis, it'll be the same on the reciprocal, which makes sense because if I take a number, a positive number like 5, and I take its reciprocal, it's still a positive number. So observation 2, f at x and 1 over f at x share positive and negative intervals. All right. Next thing, I want to talk about increasing and decreasing intervals. So, the line, if I'm reading from left to right, this line is always increasing. Let's see what happens on the reciprocal. Starting from left to right, I'm starting here, I'm going down. Then I pass the vertical asymptote, and I'm heading down again. So the original function was always increasing, but the reciprocal was always decreasing. Let's see what's happening on the parabola. The parabola starts off decreasing, but once it hits that vertex, it starts to increase. So after 1, it increases. Let's see what's happening on the reciprocal. The reciprocal is first increasing. Then it passes the vertical asymptote and it increases again until it hits that same x equals 1 value. Then it starts to decrease. So it looks like we have opposite behaviors in terms of increase and decrease. So number 3, when f at x is increasing, 1 over f at x decreases, and vice versa. Now, if I want specific points on an original and a reciprocal graph, I can just take some coordinates from the original and flip the y coordinates. So for example, let's take a point. Let's take this point here. This is the point -1, 2. When we're taking a reciprocal, we're taking the reciprocal of the y coordinate, which is the 2. So I would expect the reciprocal graph, when x is -1, y should be 1/2. Let's take a look. And yes, it is. Perfect. Okay. So that's always a way to get some points. And finally, there are two y values that if I take the reciprocal of them, the value doesn't change, and that's 1 and -1. So if I look at my function, let's say right here at -1.5 comma 1, that should be a shared point. And there it is. And same thing with the negative ones. So right here at -2.1, -2.5 comma -1, that should be a common point, and it is. Okay, so when you take the reciprocal of 1, it's the same value. So I'll make a little note. F at x and 1 over f at x share points when y equals ±1, because the reciprocal is still ±1. So let's try to take these observations and actually graph some reciprocal graphs. Let's take 1 over x squared minus 4. That's what we're going to graph. Now, I'm going to start with the original function. The original would be x squared minus 4. I'm going to graph this function. This is just a generic parabola that shifts down 4 units. I can see it like that, or I could also factor this and see that my x-intercepts are at -2 and 2. So I know that's there. From the other form, I know that the vertex should be at 0, -4. To me, that's good information, and I'm going to go ahead and connect the dots. Okay, and that was y equals x squared minus 4. Now, the first observation we made is that x-intercepts become vertical asymptotes. So my x-intercepts were at -2 and 2. Those will now become vertical asymptotes. So in red, I'm going to graph actually h of x. In blue, I just had the original function, so I can start my sketching, okay? And now, whenever the function was positive, so with the reciprocal. So I'm expecting, in this region where the parabola is positive, I'm expecting my function to be positive here as well. Positive here as well, but negative here, okay? And then I'm expecting the increasing and decreasing intervals to be opposites. So my function starts off decreasing until we hit that vertex, and then it increases. So on the reciprocal function, h of x, if I start off decreasing, I'm expecting in this region to actually increase. And then when the original function is increasing, I'm expecting the reciprocal to decrease, okay? And we know that there should be some shared points at 1 and -1. Now, I didn't find these values accurately. I just did a very rough sketch. So this is -1, this is +1. So I'm just going to take these points here and say, yes, they are shared points. There we are. And now I'm almost ready to connect some dots and draw the general shape, but I just realized I forgot to talk about an observation above. So I'm going to do that right now. Now, if you look at all of these original or reciprocals, they also have a horizontal asymptote, and the horizontal asymptote is always at 0. So observation 5, horizontal asymptote at y equals 0. The function is always approaching the x-axis, but never actually touching it. And that helps me here because I need to be increasing. I need to go through this point, and then I need to go towards that vertical asymptote. So I'm just I'm starting here where my horizontal asymptote is, and then I'm following it. I go to the shared point when y is 1, and then I follow the asymptote. Same thing on the other side. Here I should be decreasing, and there it is. In the middle, I'm expecting to increase until the y-axis and then decrease. So I'm gonna increase, and then I'm gonna increase, and then I'm gonna decrease. Okay, and there we go. Very rough sketch. Now, if I did want a little bit of one more point, let's say, I know the vertex, it's when y is -4, so the y on the reciprocal should be -1/4. So this point here is 0 and -1/4. And there we go. In red, you will see that reciprocal graph. Okay, let's try another one though. Let's do the original function is x squared minus 2x minus 8. And we want to graph g of x, which is 1 over that f at x. I'm going to start off by graphing f at x. And for f at x, I do want to factor it. So multiplies to -8, adds up to -2, or do crisscross, whatever factoring method you want. Here we are. And that means that my zeros are 4, 0 and -2, 0. Here we're just using our grade 10 knowledge of parabolas. There we are, plotted those points. And because this one wasn't in a nice vertex form or anything like that, I mean, I could do a table of values and just start subbing in some points to get more on this parabola. Or I could average the zeros to get my vertex. So I know that the vertex should take place halfway between 4 and -2. So to find the halfway, I'm just going to add these values and divide by 2, which is 1. And then I can sub into my function 1 to see the y coordinate. So 1 minus 4, 1 plus 2 is -9. So I'm going to plot that point here. Okay. Now if I could just connect the dots right here, but I could also, I didn't do it in the previous one, but because the a value is 1, I know that the function isn't going to be stretched or anything. So whatever that original step pattern of a parabola is, which is 1, 3, 5, applies to this. So from that vertex, the next points are going to be 1 up. The ones after will be 3 up, 5 up. From there, hits our x values, and then 1, 3, 5, and then 7 up. So there we go, just a little bit more accuracy on the parabola. And if you forget, the step pattern or anything like that, one, you can refresh, or two, you could do a table of values. So here's the original function, okay? Now I'm gonna start with my reciprocal, and the most important thing to start with is those asymptotes. So we'll have one at -2, the other at x equals 4, and the final at y equals 0. Okay, great. Then some shared points. I'm just going to go to 1 and -1. So actually, you know what? I'll go in blue. That's a shared point. That's a shared point here and here. I'm just finding the points on the parabola that have y values of 1 and -1. Okay, and I know that I should be positive here, negative here. So I kind of already have an idea. It should probably be something like this if I'm just trying to follow the asymptotes. But just to verify, I want to decrease, okay, on the original, which means the reciprocal should actually be increasing. So that would be very good. This would be increasing motion. This would be increasing motion, and then decrease the rest of the way. Now, if I do just want to add one more point, I'm going to take this one here. That point is 1, -9. On the reciprocal, it'll become 1, -1/9. So just very close there. And now I'm going to increase towards this point and increase towards the asymptote. Then I'm going to increase towards the common point towards the reciprocal of the vertex. And now I'm going to decrease the rest of the way following the asymptote. And here, follow the vertical asymptote to that common point, and then follow the horizontal asymptote. And there we go. F at x is in black, and g of x, which is our reciprocal, is in blue with the red asymptotes. And there we have it. So x-intercepts become vertical asymptotes. The horizontal asymptote is always at 0. The positive and negative intervals perfectly match, whereas the increasing and decreasing intervals do a full-on swap.